Assalamualaikum and good day. So now I will continue my lecture for chapter 6 that focusing on the sub chapter 6.6 which is transformer protection. Okay, this is the outline for chapter 6 as we know, and today I will continue my lecture for 6.6 that focusing on the transformer protection. As we can see here, when a transformer is energized, a transient overcurrent is created, which depends on the moment that the voltage is applied and the permanent induction of the magnetic circuit. Okay, as we can see here, this is the curve for the energization of the transformer. As we can see here, this is the I in rush versus time. And we can see the trend of the graph is the exponential, and this is the I in rush that happened during the energization of the transformer, and this is due to the transient overcurrent, and this is the formula for the I in rush, and we can see here that the inrush current is depends on the damping time constant, which is tau. Okay, here is the formula. Okay, from the exponential curve. Okay, the peak value of the inrush current is damped according to an exponential law. Okay, this is the formula. I rush in time is equal to I rush exponent T divided by tau. Okay, which is I rush time is a peak value of the current in relation to time, and the I rush is the maximum peak value. Okay, for example, the first peak of the curve, and then tau is the damping time constant. Okay, then from the formula we can get the maximum peak value, which is defined in relation to nominal RMS current of the transformer, which is I rush divided by IN. Okay, this is the maximum peak value, which is the ratio of I rush with the I nominal. Okay, table shown here is the inrush current on high voltage side of liquid insulated. Okay, this is the liquid insulated transformer. As you can see here, this is the power in kVA of the transformer, and the rated is increased from 100 to the 3150, and then this is the ratio. Okay, the ratio of the inrush current to the nominal. Okay, we can see the value is decreased. Okay, so as a conclusion for liquid insulated is the ratio is decreased when the power is increased. Okay, here is the table for inrush current for dry type transformer. Okay, we can see here is the dry type, and also we can see the power is increased from 160 to the 2000, and this is the ratio. Okay, ratio of the inrush current to the nominal current, and we can see that the value is almost the same even the power is increased. So it means that the ratio is maintained for certain value. This happen for dry type transformer. Okay, here is the specific protection against overloads of the transformer. Okay, first is we have to monitor the temperature of the dielectric for the liquid insulated transformer, and generally we set the temperature for the threshold alarm is the 80 degrees Celsius, and this one is for energization, and then for the de-energization condition, when we offload or we switch off the threshold of the transformer, the temperature is a little bit higher, which is 90 degrees Celsius. This is because there are some transient happen during the de-energization, and so that we have to increase the temperature a little bit higher. Okay. The next is we have to still monitor the temperature of the dry type. Okay. The process is same for liquid or the dry type insulation. And also we have to consider the long time delay trip relay on the circuit breaker installed on the low voltage side of the transformer. And also we have to consider the thermal overload protection of the transformer. Okay, here is the specific protection against internal phase short circuits. As we can see here, this one is for transformer with a liquid insulated. Usually the liquid insulated is the oil insulated here. And we can see here that this is the transformer tank, which include the winding of the transformer inside this tank. And here is the Bushu relay. Okay, this relay is connected between the oil transformer, oil tank transformer, and also the transformer tank. Okay, the purpose of this Bushu relay is to trace or to trace what happened inside the insulation here. As we can see here, when the transformer, this is the flow from the transformer tank, okay, and then this is the flow to the conservator tank, which is the oil tank here. Here is the Bushu relay, and as the transformer operate, there are some heat inside the dielectric here, inside the oil, so that the heating will energize some gas or discharge of gas caused by the short circuit if the fault happen here, so that the float here, okay, will trace the gas that trapped here inside here, and then will energize the Bushu relay, so that this Bushu relay will protect the transformer from the short circuit. Besides that, we also use differential protection for the transformer. Okay, here is the specific protection against earth faults of the transformer, and we have to consider that the protection against tank earth leakage fault. Okay, then also we have to consider the earth fault protection located on the upstream network, which located at the primary side of the transformer. And then we also consider earth fault protection located on the neutral earding, which the connection is at the secondary side of the transformer. And then also we have to consider the earth fault protection located on the incoming bus bar of the transformer. So lastly, we have to consider the restricted spot differential protection for the transformer. Okay, here is the diagram of the line which connected with the transformer here. Okay, there are two sides of the transformer, which is the MV side at the primary side, and also the secondary side is the LV side. So for this transformer protection, we have to put the protection for both sides to protect of the MV side and also the LV side of the system. Okay, first we go to MV side. Okay, we can see here, this is the MV circuit breaker. We can see here the types of the MV circuit breaker is equipped with a double threshold independent time protection. That is the types of this transformer protection. And we can see here there are the double threshold mean that the setting of the transformer is we set into two settings. The first I is for the smaller current smaller value, and another one is for the higher current. So means that when there are fault occur and the higher current provided, so that the protection will release and the circuit breaker will operate very fast. So means that there are higher current here to trace and to give the signal to the circuit breaker to operate very fast. Okay, that is the double threshold independent time protection. Okay, this one is connected at the primary side, which is MV. Okay, then for LV, we can see here there are one circuit breaker here for LV. And then also we have here is the secondary LV circuit breaker that protect the line or the system. Okay, next here is the high threshold. Okay, this one is for HV side short circuit inside the transformer. Okay, this one is for high voltage side. And as we know that the threshold for the HV side is double threshold. And the high threshold, high set for high voltage side must be set as must be set such that the HV minimum short circuit current cause the circuit breaker to be tripped. And also the protection must be checked to make sure that it is not activated during transformer energizing. So means that the protection only operate when the short circuit happen. Okay, this is the setting, okay, of the high threshold of the transformer for high voltage side. Next is the low threshold. Okay, this one is for LV side of the transformer. Okay, LV side short circuits. And selectivity with a secondary LV circuit breaker is time graded. Okay, we have to set the time according to the standard. And then the low threshold, I low set for transformer must be lower than a minimum value of the current detected by the HV protection upon occurrence of an LV short circuit. So the value must be lower than minimum value. Then it must be higher than transient current due to the motor startup currents or higher than pickup currents following the fault clearance on the network. So means that the setting for LV side threshold must be lower than the minimum value of the current detected and also higher than transient current due to the motor startup. Okay, here is the condition required, the low threshold to comply with the standard. Okay, this is the setting for the low threshold of the transformer. Okay, as we can see here, okay, this is the diagram of the setting of the transformer protection. Okay, we can see here the red line is for HV protection, and also the blue line represent as the LV protection. Okay, first we go to the HV protection. We can see here for HV protections there are two thresholds. Okay, the first one is this one is for the higher threshold, and this one is for the lower threshold. So for the higher threshold will protect for the higher current for the HV side, and then this one is protect for the lower current for the HV side. Okay, and then we can see here the setting is the for higher is set between I short circuit maximum from the LV side and also between 0.8 I short circuit minimum for the HV side. Okay, that is for the higher threshold. And for the lower threshold, the setting is set between the TR is the I transient, and also between I transient and 0.8 I short circuit minimum for LV side. Okay, then we go to the LV protection. Here we can see that the blue line, okay, the blue line is for represent as the LV protection. Okay, this one, this is for the independent time protection for LV side, and this one is the inverse time. The types of the protection is the inverse time relay. So this inverse time will operate faster compared to the independent time protection. Okay, this is the time interval you can see here between the low voltage side and high voltage side. Okay, here is the abbreviation for the diagram and also the meaning of the abbreviation. As you can see here, and this is also the abbreviation and also the meaning represent the diagram. Okay, next is the differential protection of transformer. And for differential protection, the scheme is to compare the sum of the current entering the protection zone to the sum of the current leaving the protected zone. So means that for differential protection is the differential value of current between entering and leaving the protected zone. And then the percentage differential relay with harmonic restraint are used for transformer protection scheme. Okay, and then this relay operates on a percentage ratio of input current to true current known as the slope of the relay. For example, the relay setting is 15%. So that means that 50% is the differential value between current entering with the current leaving of the transformer. So when the difference between the incoming and outgoing current exceeds 50% and is higher than the relay minimum pickup. This is the setting for the differential protection relay. Okay, here is the differential protection of a delta Y transformer. Okay, as we can see here, okay, this is the transformer winding. Okay, for primary side, this one is for primary side, and this one is the secondary side. And for primary side is connect in delta connection, and for the secondary side is in star to ground connected connection. Okay, this is the CT, okay, current transformer for the secondary side, which is connect to delta. Okay, the connection of the CT must be opposite with the transformer winding connection. So same goes with this CT, which is connect in star connection, which is opposite with primary side, which is delta connection. So as we can see here, I see here IB and IA here, the capital letter is represented as the I phase, and this one is the line current. Okay, for primary side, the line current is minus IC with IA for line 1, and line 2 is IB minus IC, and line 3 is IA minus IB. Okay, while for secondary side, the phase current, which is IC, CIB, and IA in small letter, is equivalent to the, is same to the current at the current transformer. Okay, because of the Y or star connected. This one is because of the delta connected. Okay, then we see here, this is the relay, which is represent as R and O. R represent as the restraint coil, and O represent as the operating coil. So the O is connect to the common here, okay, and then R is connect to the live or the line of the current transformer. So this is the operation of the relay for differential protection of delta Y transformer. Okay, next we go to example 6.7, which cover transformer protection. Okay, referring to the previous slide that illustrated a differential protection scheme, a 100 kVA step down transformer is connected in delta ground star configuration with voltage level of 3.3 kV step down to 415 volts. A percentage differential relay with 5% slope setting is utilized for this overcurrent protection scheme. The primary side current transformer ratio is given as 5:1. Okay. First question is find the value of secondary current transformer ratio. And then second question is identify the differential percentage between the incoming current and the outgoing current. And the third one is propose the minimum secondary current to active the percentage differential relay if the primary current is assumed to be constant. Solution for example 6.7. Okay, first we have to find what is the current at the primary side. Okay, at the primary side, IP is equal to S divided by Z3 divided by 3.3 kV, which is equal to 17.5. Okay, this is the I at primary side. And then we have to calculate what is the current at the CT at the primary side, which is equal to IP times with the ratio of the CT, which is 1/5. We get the value is 3.5 amp. This current is the value at the CT at the primary side. Okay, then we have to measure what is the current, okay, IA at the I phase. This is the I phase at the primary side, which the value of 3.5, the value at the current transformer divide by Z3, because the connection of the phase is in delta connection. So we have to divide by Z3. So we get the answer here is 2.02. This is the current phase at the primary side. Then we repeat the calculation for secondary side, which is we have to calculate what is the I secondary. Okay, by using the same formula S divided by Z3 divided by V, which is equal to 139.12 M. And we have to calculate what is the ratio between secondary current and primary current. And we get the value here is the secondary value, and this one is the primary value at the winding, which is ratio is 68.87. So the proposed value for the secondary current transformer ratio is 70. So we have to choose the nearest one. Okay, next is the solution for questions number 2. Questions number 2 need us to identify the different percentage between the incoming current and the outgoing current. So first we have to calculate what is the IA. IA is represented as the I phase, okay, at the secondary side. Okay, this one. Okay, I phase is equal to I at the secondary, okay, times with the ratio of the transformer, current transformer. Then we get the I phase is equal to 1.99 M. This value is the I phase at the secondary side. Okay, then we have to calculate what is the I at the current transformer at the at the secondary side. So the secondary side, the transformer is connected in the Y connection. So we have to times with the cert3 to get the I at the current transformer. So which is 3.45 M. IO is the I operating, as I explained at the previous slide. Okay, IO is the I operating of the relay. IO is the difference between the primary side and the secondary side of the current transformer. So we get the ratio is 0.05. This is the difference between the current transformer value at the primary and the secondary side. That is IO. Then we have to calculate what is the IR. Okay, IR represent as the restraint. Okay, which is the average of the current transformer at primary side and also the secondary side. So we have to total up all the primary and secondary side divide by 2 to get the average value, which is equal to 3.475 M. Then we have to measure what is the percentage. Okay, the different percentage. So the different percentage is equal to the IO, which is I operating divided by IR times with 100, which is equal to 1.44%. Okay. Okay, next is the solution for questions number 3. So questions number 3 need us to propose the minimum secondary current to activate the differential relay. Okay, first we have to know what is the X. Okay, this is the X value. X is represent as, we assume X is equal to I small ia small capital small letter minus IB small letter. Okay, this is the current transformer value at the secondary side. Okay, the small letter is for at the secondary side. So we use the ratio, okay, the average formula to get the value of X. Okay, X is represent as the different the value at the current transformer at the secondary side. So by using this formula, okay, IR, and then we get the ratio is equivalent to 5%. This is given in the questions. Okay, sorry, this is the setting. Okay, the setting relay is differential relay is 5%. So by using this formula, and then we get the value of X is equivalent to 3.33 M. Okay, then we can get the I secondary, okay, is equal to the this formula. So we have to times with the ratio of the CT, okay, which is 70. Okay, then divide by cert3 because the IS is in the star connection. So this is the value. Okay, I think that's all for subtopic 6.6, which cover about transformer protection. That's all. Thank you.